Our next technical talk is another CERIAS student, Daniel Mitty, who is in computer science and is a PhD candidate here. Daniel?
Thank you very much. So good afternoon, everybody. Thanks for being here, and thanks to all the CERIAS organization for hosting me. My name is Daniel Mitty. I'm a PhD student. I work with Professor Bertino on security techniques for sensor systems and the Internet of Things. For the particular work that I'm going to present today, I work with Professor Payer as well, one of the new additions to the CS department. Very, very welcome and very appreciated. And he was in one of the panels earlier. What I'm going to talk about today is a project called nesCheck that deals with memory safety. So ubiquitous computing, and the panel right now was really interesting for this purpose, is now definitely a reality. Wireless sensor networks have been around for quite a long time now, and all those sensors are really, really widespread for a variety of reasons. I mean, they're small and cheap, and so you can find them. They found a good purpose for thermostats, industrial settings, precision agriculture. The agriculture department here at Purdue has a lot of actual good uses for those sensors to monitor the soil composition, the humidity, the light, and the temperature. So they have a really wide variety of usages. And the Internet of Things, as a generalization of it, is really, really picking up pace right now. And with all those small systems, they are, however, in some cases quite powerful and always on and connected to the internet. Security becomes really, really paramount. And a lot of policy side of it have been discussed in the panel just now. However, from the system perspective, like concretely, some of the requirements that are really important are having reliability for the system end-to-end in whatever way you want to achieve this, having data delivery that is actually trustworthy and data actually gets to the destination untampered with and with all the correct measurements, and that the service in this case has to be available as much as possible for the whole time. And this particular work will focus on wireless sensor networks. So we'll see that we're talking about sensors that are significantly smaller, less powerful, and with way more like stringent constraints. So wireless sensor networks have to be functional at all times. However, they have a lot of problems in trying to achieve security. They communicate on an unreliable wireless medium. They have constrained resources, and they usually operate in an unattended environment. So those sensors are just deployed with no tamper-proof packaging, and anybody can steal a node, reverse engineer it, actually analyze it. So this can easily lead to failures that are both transient, and so they disrupt the service for a little while, or even permanent, and they can cause a real damage. Some of the security threats of this connected world, wireless sensor networks are susceptible to attacks from a lot of different entry points. So packets and network traffic, device resources, actual network routing. And while you can think that attacking a deployment, for example, for agriculture, might not make many victims apart from some economical interests. Well, earlier we were just talking about hacking pacemakers, and so there's actually a lot of possibilities to do real harm to people's safety. So if you're automating using sensors for a hospital, you can give a patient the wrong treatment with a security breach. In a smart city, a lot of those sensors, for example, control traffic lights. And if you have a wide area blackout, well, the consequences can be pretty bad. So for wireless sensor networks, a really widespread operating system that is the one I've been working on for this project is called TinyOS. And those applications are often critical, but as we said, achieving the big three of security, reliability, integrity, and availability, it's really hard. And TinyOS is this sensor network that tried to make, it's this sensor network operating system that tried to make sensor network development as easy as possible. And it is, all those applications are developed in languages that are low-level languages. So we're talking about C or other dialects of C. Those languages have no memory protection. And whoever has written any single, even small piece of code in C knows that it makes it actually, it makes it really easy for you to write code that will have memory problems. Now, I want to bring everybody up to speed on memory vulnerabilities, which will be the focus of this work in my talk. I'll just give a really quick introduction on a couple of attacks that can happen at the memory level. So the outcome of a memory corruption can have a wide range of outcomes. The nodes, those little sensor nodes, can just crash or reboot, and no big deal. It's just a transient failure. You can start actually processing and disseminating incorrect data. So if you're trying to measure the temperature of the soil in a huge crop, for example, you can start making serious business decisions based on data that is completely skewed, and slowly degrading the functionality of your network up until it's actually not really useful anymore. But it can get much worse. So what the problem is with memory vulnerability is that it's quite easy to get to the point of having those sensors execute arbitrary malicious pieces of code that somebody can try and inject in otherwise benign software. And there's a couple of different ways, more than what I'm listing here, to do this. In general, the code injection attacks or other techniques are return-oriented programming. You're reshuffling pieces of existing code in order to make a program do what you want it to do and not what the original programmer intended for it. And so in the news, there have been a lot of actual concrete incidents in which memory corruption attacks have led to a lot of problems. And I was gonna mention the pacemaker again, but I was preceded by the panel already on that. But that was a very serious incident. One that I thought it was really funny when it came out and more related to the IoT. Last year, a smart refrigerator was found sending spam emails. Was a spam server for some malicious attacker, and so they found, analyzing the traffic, that the refrigerator in somebody's house was actually spamming other people, which I thought it was pretty hilarious. And so, in general, having appropriate measures to protect the functionality of wireless sensor network becomes really paramount. Now, to see what a memory vulnerability actually is from the technical point of view, and technical people, please bear with me for a couple of minutes. Let's look at what a buffer overflow is, one of the basic types of memory attacks, memory corruption, how it works. So for this simple example, what I want to do is to go through. I'm assuming that I try to register to the CERIAS symposium, and I'm playing with a little kiosk in order to go ahead and register. In the top part of the screen, I'm going to show what's the interface that I interact with, and in the bottom, I try little zeros and ones. So that's supposed to be kind of a simplistic vision of what the memory of the device is at that state. So we have a couple fields. All the data is stored in fields in the memory, and the programmer has to choose at the very beginning how big those fields are. So you can be on the safe side and say that to store the full name of somebody that is registering, maybe 100 characters will do. Some foreign language names will disagree with that, but you can never be too safe. Anyway, in this case, we have a field for the full name and a field for the age. And in memory, they often happen to be one next to the other. So what happens is this kiosk is letting me register, and it tells me that if I'm 21 years old or younger, I can get in for free. So the first thing that it asks me is to swipe my ID in the kiosk, and so I do that, and it reads my age, and it reads that my age is 27, and it puts that in the little age field in memory. And then it tells me, please enter your name in the little text box. So I put in my full name, I press enter, and in memory, that information is actually copied in there. And well, not very surprisingly, the total that I owe is not free. I have to pay, let's say, $10 for this. Now, if I am a security researcher and a bit of a freeloader, then I might want to try and circumvent the system to try and get in for free anyway. So what I do is I'm like, that's fine, let's start over. I go ahead and swipe my ID again. My age hasn't changed. I haven't aged since the first time I swiped, luckily. And when it tells me to input my name, Well, what I do is to put in a really, really long string, well-crafted, so that I can try and circumvent the system, and to see if those programmers for this kiosk actually thought that somebody might try to play them. When I press enter, this information will be copied in the full name field, and unfortunately it will be so long that it goes up over the boundaries of the field, and it spills over the next field. So what I did is, providing a string and just interacting with the system, I was able to alter the memory so that some other information has been tampered with. The kiosk developer thought that, well, we're really smart. People have to swipe the ID, and they will never be able to, circumvent the system. But now I owe them $0, and I can get into the symposium. So this is some sort of simplistic, example of how a buffer overflow works. And you may think that, CERIAS without those $10 hopefully will not go bankrupt unless everybody starts doing it. However, how this translates to actual code and how it works is that usually in memory there's fields for data, and there's fields also for control flow to decide what the next instructions will be. And so a simplistic layout of an actual memory of the program can look something like this. I have a little field for some data, let's say a message, a field that holds what the next actual instruction to be executed will be. Let's say it's instruction at the address 1234. And then there's the code. So right now the flow is fine. If I do the same trick of trying and writing too much and overwriting, what I can do is to inject some evil code, some malicious code here, put some padding so that we get to the point I want, and then also overwrite what the next instruction address will be. So all of a sudden, the next instruction is not what the programmer intended, but it's some code completely arbitrary that I injected. Now, I hope I convinced you that buffer overflows are scary. I will try to scare you even a little more right now, just because in wireless sensor networks, one of the important characteristics is that all of the nodes of the network run the exact same image of a software. The exact same software runs in the same way with the same memory addresses on all of the nodes. We can think of a network of 5 nodes. We can think of a network of 1,000 nodes. If I find one vulnerability in one node, this is a realistic picture of me, obviously, I can craft a specific network packet that I just send to whatever nodes I have in my vicinity. I am able to corrupt them with that vulnerability, that one vulnerability, and tell them to just keep propagating and keep infecting the whole network. This is not only feasible and not too hard, but it's actually been shown for all of the available sensor architectures out there right now. So why is this relevant? This has been an issue, not just for sensors, but for software in general for a long time now. And the problem is that for regular platforms, a lot of research has been done, and a lot of the common techniques that have been developed require a lot of additional memory, a lot of additional resources, virtual memory techniques. Those sensors don't have those characteristics. They just don't. And so in some cases, they have a really high overhead, and these sensors sometimes process real-time data that has to go pretty fast. I can't slow them down too much. So a big overhead is also a big no-no in this sense. However, let's try and go back to the bright side now that we're really in a dark place. There's a lot of advantages to this sensor software. They're usually, the code size is small, and it's very modular. It's focused on doing one task and doing it well, and the whole program is available. For TinyOS, even the operating system code is included and compiled all together in a single image. So there is no dynamic library to be loaded, something that I didn't expect to happen. So this can actually be used to our advantage when designing a defense strategy to use advanced language-based techniques that know everything a priori. And also, the thing is, we see that the problem is when I'm trying to access the memory. I either write or read from the memory. So one could say, well, just check every time that you touch the memory, check that you're inside the boundaries of whatever field you're dealing with. That can have really, really high overhead and slow down. But not all of those checks are needed. If I have all of the code available, what I can do is to determine, well, some of these memory accesses will never result into any problem or an attack. And so I don't need to slow down the problem that much. So this was all the basis and the premises for nesCheck, which is the work that I developed with Professor Peer and Professor Bertino. And what we do is we combine static analysis and dynamic instrumentation to, at static time, try to find all of the possible bugs that we know and are known, as well as provide memory safety guarantees with the lowest possible overhead whenever I can see that a check will not be needed, because I can statically prove that that piece of code, that memory access, will always be safe. So there's a lot of applications, and we can think of corporate devices, but also consumer devices. So extending this to the Internet of Things, this can help protect the Nest thermostat that is trying to break loose into your home network. So some of the goals of our work were to find bugs. I call bugs what is actually a bug from the developer. No matter what input I try to give to that kiosk, a bug means that all the time the program will crash at that particular memory access. Then I try to find all the vulnerabilities, which means all the memory accesses that potentially, depending on the input, could lead to a problem. And iteratively, I remove all the checks that are not needed and the ones that I can say, well, this memory access is safe. And I insert all the checks. These are the static goals. And dynamically, I protect with a check all the accesses that could lead to a problem. And so I will catch whatever attempt to break into my memory. The TinyOS operating system is developed in nesC, which is a dialect of C that has a couple extra features, but for the most part is C. And the normal toolchain works as you take the nesC source code, you put everything together, the network stack, the operating system, your code that you wrote, you compile it, and then you use GCC, the C compiler, to output for the target platform, for the sensor. What we do is to leverage LLVM in the middle. The LLVM is an open source compiler and optimizer. And what we do is to add a sequence of steps proprietary to our particular system that will take care of working on an abstract representation of the code, do type inference to classify all the pointers based on how dangerous they are, calculate metadata and use that metadata to reduce the checks, and finally produce all the dynamic runtime checks. So to give a glimpse of the big static part of the work and the big dynamic part of the work, what we do is we use a type system to classify all pointers and memory accesses into 3 categories. Safe pointers are the ones that will never result in a memory error. Sequence pointers are the ones that could. And dynamic pointers are the ones for which I actually don't know anything. They could contain any type of information, any data type. And we use, just as a little snapshot of the algorithm that we use to classify, all accesses, we consider them safe at the very beginning. And then going through all of the accesses, if I do any sort of pointer arithmetic on that particular pointer, I could potentially go out of bounds, and so I call it sequence, and I make it potentially vulnerable. If I do weird operations with those pointers, like casting an integer into a string or vice versa, or into a pointer, which is, by the way, totally legal in C. There's nothing against it. It's fun to try and get the standard of C and find that some of those operations are legal and their result is defined as undefined behavior. That's how they define the standard. And I classify those as dynamic pointers. I keep track of some data about all the memory areas that those pointers point to. So how big are those fields? How much I can move in one direction or the other? During my analysis, I keep all the metadata in memory of my particular tool to try and not add any overhead to the application at the beginning. And for example, for each pointer I see, it points into the memory somewhere, and it can freely move in its allotted space, SL to the left and SH to to the right, for example, and not more than that. In some cases, I need some variable might have some pointers might point to different parts of the memory depending on how the code, whatever path the execution of the code takes. And so in this little simple example, I have a pointer p. That pointer will be given a different amount of memory depending on a variable that is provided by the user, that variable a. So what I do, I don't know how big p will have as a space in the memory. And what I do is to add, my tool will add some explicit metadata holders to say, well, depending on the path, I'll keep track of whatever choice you made before and make all of my decisions about the checks at runtime based on the actual dynamic runtime execution flow. In the very last case, sometimes having an additional variable cannot be enough. I'm thinking about pointers that are inside structures, pointers that are pointing to the heap and they are passed around through various casts. So in this case, I might have to use an explicit metadata table in memory, which is what makes a very high overhead for a lot of the techniques for regular PC software. So this is something that in some cases is just necessary. On the dynamic side, what I do is in LLVM, the memory accesses are get element pointer instructions. And well, that's when I'm calculating which memory location to access. And any vulnerable, I insert all my checks before all the vulnerable accesses right before that particular instruction. The reduction is done by checking all the metadata that I have collected up to that particular point in the code and combine it with whatever type that pointer was, whatever usage I've tracked so far. And if the check will always result at that point, I can see it will always tell me, sure, this is safe. That is a check that I can safely skip and not add any overhead, any additional instruction onto the program. So I will go quickly through some of the evaluation results of my software now to start wrapping it up. We ran our software on 10 standard applications that come with the TinyOS operating system. They're open source applications. We weren't expecting to find many actually memory bugs that have been around in the community as open source for something like 20 years. So any memory bug, I'm going to say has been caught already. The caveat is like hopefully has been caught already. But we can probably say that. And we can see that just looking at how all the pointers on average are classified, the vast majority of memory accesses in a sensor application will be safe. So I will not need any particular check or extra care for that pointer. This lets my technique and my tool have a really low overhead. And out of those that are not safe, my tool is able to determine that 18% of those checks are actually useless. And so I can safely skip them. We keep reducing and shaving a little bit of the overhead necessary for that. What I do measure at this point, once I actually run my tool on the code, is to see what is the overhead in terms of code size, in terms of memory usage, and in terms of performance. So how much do I slow down the execution? On code size, the average is usually 6.9%. In this case, for all of across all of our benchmark. And you have to think also that these are bytes. Like those applications are really tiny. So this is about 350 kilobytes for something that contains operating system and network stack. So an increment of 7% is quite reasonable to have full memory safety. From the performance point of view, the slowdown on average that we observed is 2.8%, and we go up to a slowdown of 8.4%, which is very competitive with a lot of much bigger overhead techniques for PCs and traditional systems. And for the memory point of view, it really depends on what kind of data that application deals with. We go as low as an overhead of 7%. And in all of the cases that we analyzed, we never went above the 10 kilobytes of total memory. 10 kilobytes of RAM is just so little that the little sensor platform that we were we're dealing with has, which are the Telos B modes for anybody that's doing sensor sensor network research or work. To wrap it up, I want to just highlight a couple good points about my technique and a couple points that are future directions for the work and stuff that I'd like to improve. So we have a really low overhead, and this is because a lot of the heavy lifting is done at compile time. And I don't require any source code modifications. There are other techniques for sensor networks and TinyOS out there that require the programmer to go through all of the variables and the pointers and declare exactly how much space, how big the memory area will be for those pointers. That is a huge amount of work. And that has been, it's one of the first effort in that direction. It was called Safe TinyOS. It's still very good, but it has a really lot of, a big burden of effort on the developer. Also, I put it in tiny, but I think it's really important. I work on an LLVM, which is, I work on top of an intermediate abstract representation of the code. That means that I can apply this technique, if I want to any source code. I'm completely agnostic to that, as long as LLVM supports it as an input language. And I can directly apply this to any hardware, even without any memory protection, just because we don't require virtual memory. We don't require anything additional like that. So it's very suitable for constrained device. Points of improvement, so little minus signs. Failure handling, whenever whenever somebody still tries to attack the application, it's protected. I will not let them corrupt the memory. However, as of now, when a check fails, all I can do for real is to reboot the node. I will just stop the execution then and there. I will not let them propagate false data or do malicious attacks, but I have to reboot. So it might be a slight disruption in the service. What we want to look into is to give the programmer some the possibility of deciding what exactly happens when a memory corruption still tries to verify. No temporal safety. What we talked about so far is called spatial safety. So I go out of the allotted space. We can do this also in time. So let's make it even scarier. We can do this also in time. An attacker can try to access data that was used in the past in the code. And so theoretically, that memory should be unused and reallocatable. However, somebody can try and read that information and leak it out. We don't address this in the current prototype. We probably don't need to, because those sensor systems don't have dynamic memory allocation for the most part. But we would like to investigate into it just for the system that do have dynamic memory allocation. And the last part is how well do we scale to bigger code bases and that can be run on more powerful platforms. We want to investigate if there is the possibility to use formal verification techniques to give a mathematical formal proof that this software will be memory vulnerability free. So these are the pros and cons, and I thank you so much for listening to me, and I'm definitely open for questions if you guys want.
Hey, Daniel. Nice talk. Vijay Raghunathan from ECE at Purdue. Two questions. One is, I thought you mentioned the memory overhead.
Mm-hmm.
By memory overhead, I presume you mean the RAM overhead.
Yes. Yes.
And you said that the memory overhead is always less than 10 kilobytes. Is that correct?
The whole memory that we use. So it's the memory that was used by the program originally plus my overhead. It's always within the 10 kilobytes constraints of the platform that we were using.
And could you, what is the memory overhead that your technique sort of adds? It says as low as 7%. That seems to be the best case. And
yes.
So what is the, could you indicate what the average case is? Because I know that 10 kilobytes is the total amount of memory that this microcontroller has, the Telos microcontroller has.
Right, exactly. So it's really ugly to present an average just because there are some cases in which some programs natively use 6 bytes of memory. And I have to store 3 pointers, just 3 pointers. That adds up to 24 bytes. So my overhead in that case is about 400%. So presenting the average, it looks like it's gigantic. However, I'm adding 24 bytes on top of 6. So if you just do the relative percentage, It looks gigantic, but it's 24 kilobytes. It's hard to represent it as an absolute measure. But so yeah, there's some cases in which I have more overhead than what the original program used, just because, for example, the network stack always will require some pointers to be stored in the memory.
So just as a visual illustration, so on this graph,
Yes.
are the black lines your instrumented code and the green lines the original application?
The black line is how much memory the original application used, and the green is what I add on top of it.
Okay.
I just put them one next to the other to compare, the relative size of it. So, if I use 3,500 bytes of memory and I add 500, it's not terrible. Oops. But in this case, if you were to do a percentage, it's really a really bad number. But
got it. I was just looking for a visual representation.
No, thank you.
That's good. The second question
Yes.
I had was, given the fact that an increasing number of microcontrollers that are being used in IoT devices or sensor networks have now memory protection units or MPUs built into the hardware. What implications does that have on a technique like this? I mean, does that in some sense make some of these techniques redundant or not required anymore?
For some of those controllers, yes, absolutely, that is true. The thing is that those are usually used for something that you don't want to have 10,000 copies of. So if you use that microcontroller to power a thermostat, for example, like chances are you're going to have one of those, and that's going to cost you about $300, something like this. If you have to deploy this for a healthcare application to collect, like, humidity across the hospital to make sure that everybody is comfortable, for example, you might want to spend a really little amount of time and have a dumb chip that does only one thing. And there's still the chance that somebody's going to try and hack that. I don't know if this answers your question.
Well, yes, we can take this offline, but
sounds good.
Kind of.
That's a very good point. Yes, thank you. Any further questions? Or very tired after a long day? All right. Thank you very much again.